All right, I did a couple more problems that I think are good practice for understanding acids and bases. I chose 56 and 58. Hopefully you had a chance to work on them yourself and compare and have a use this video to compare your answers to. I think the amino acids are interesting because in a way they're diprotic with the little difference from most diprotic acids that you have protons that are in very different categories. You've got protons attached at the amine end of the amino acid and then the carboxylic acid group. So this question asks about what is the dominant form of an amino acid at some different pHs. Because we have weak acids, weak bases, it's helpful to use the Henderson-Hasselbalch equation, which you remember gives you the pH if you've got a significant amount of a weak acid or weak base and its conjugate. And all you need to remember is that the pKa, the acid form of the couple, is one term, and then you have a log of the ratio of the base conjugate over the acid conjugate. As I mentioned in class, these values can either be concentrations or amounts of moles. So for glycine, which I have drawn above, we have the pKa values, and we're asked to figure out what form the amino acid is under the different pHs. So here, let's do the Henderson-Hasselbalch equation for each side of the molecule and see what the ratio that comes out of it is. Hopefully this will become clear as we move along. So if we're saying that the pH is 1, what's the predominant form of the acid part? And so I'm just going to plug in the appropriate components. I'm sort of shorthanding here just the acid side of the molecule. And if you solve for this ratio, you end up getting 0.050 for this ratio. So the dominant form of the carboxylic acid is the acid form. That's not a big shock when the pH is 1. When we do the ammonium side of the amino acid, frankly, I'm not sure if I'm saying ammonium is the correct lingo for that. But if we take, in this case, the base form over the acid form and solve for that ratio, we're going to see a really teeny number. This is not a shock at all. And so the acid form is going to be predominant. So I'll just summarize those two calculations with a single little sketch here of the molecule. So the predominant is both sides of the amino acid in their acid form. If I do Henderson-Hasselbalch at a pH of 7, let's see what we get. So for the carboxylic acid, the only change we make is on the left-hand side of the equal sign. And again, we're going to have the log. Whoops, made a little error. It's pretty tough to make it through these things without making any errors. Plus the log of the base part of the couple over the acid part of the couple. And that value turns out to be a pretty large value. It ends up being 5.0 times 10 to the fourth. So at a neutral pH, what this is telling us is that essentially the acid group is giving up most of its protons to the solvent, basically water. For the amine side, again, maybe I should write it this way. We don't have an acid, and I really should say we don't have an acidic enough environment to strip off the proton from the ammonium side to any great extent. This is 2.5 times 10 to the minus 3. So there's far more of the acid form for the base compared to, this is mostly the acetate form. So the predominant form of this amino acid has the positive charge on the amine side and the base form on that side. And then what do you expect is going to happen when we have a very, very basic solution? I think you know what's going to happen, but let's prove it with the math. Here, the pH is 12. The pKa of the acid is 2.3. I have the log of the base component over. Notice how my handwriting gets worse as I go along. And if I solve for the ratio, I get a huge number. It's not a shock at all that hardly any of these carboxylic acid pieces survive in such a basic solution. And then what do we get for our work? That's the base form. Here's the acid form. And solving for the ratio gives me a value of 250. So there's far more of the base form than the acid form. So the predominant form of the amino acid is missing protons from both ends. There you go. A very brief problem I thought was useful to do. I just want to mention that it's important not to think of these concepts that we're learning over the course of the semester as, inside a pretty box with a bow on top and they don't cross over at all. We learned a lot about thermodynamics earlier in the chapter and equilibrium constants. Here's an opportunity to take the idea of enthalpy and equilibrium constants and apply it to an acid problem. This question is asking about considering basically the thermodynamics of water dissociation. Offhand, I don't have the page number in your book, but there's a small little section that mentions that different values of Kw are true depending on the temperature. At 273 Kelvin, or 0 degrees Celsius, we have a Kw of 0.12 times 10 to the minus 14th. If the water is warmed up to boiling water, we have actually a larger value for the Kw at 373 K. Really, there's two different ways to get at the delta H. The most straightforward is just to use essentially 2 points, using the Van't Hoff equation, a really powerful equation. That allows us to find out the equilibrium constant at a temperature other than one we already know, or to actually find the delta H itself. So the unknown in this equation can be in a variety of places. 8.314 joules per K mole. And I want to put, I'll have my K1 be 273 minus 1 over 373. Did I get this right? I hope I did. And on my notes, I apparently solved it and must have gotten a correct answer from my manual to show that this is a positive delta H. So this is an endothermic reaction. Or I could rewrite this as 52 kilojoules per mole, positive. So as is indicated with the values of the Ks, as you warm up water, you actually cause, you enhance the dissociation. So you could think of heat as a reactant based on the positive value of the delta H. Hope this helps. Work hard on the problems I assigned for Monday, and we'll press further into kinetics as we go along. Take it easy. Bye.